Low voltage issues in a building can arise from various factors. Some of the most prevalent causes include loose or corroded connections which increase resistance, and drop voltage, overloaded circuits where the current demand exceeds the circuit's capacity, faulty equipment that draws excessive current or malfunctions, and problems with the power supply itself, which could be internal or external to the building. In this particular case, the fact that the low voltage is affecting several different panels points towards an issue originating at the main service. This is because the main service is the common source feeding all the downstream panels. To effectively troubleshoot the problem, firstly check the voltage at the main service panel using a voltmeter. Compare the measured voltage to the expected voltage, typically 208 volts, 240 volts, or 480 volts depending on the building's electrical system. If the voltage at the main service is significantly lower than expected, the problem is likely originating from the utility company's supply. Contact the utility company and report the low voltage condition for them to investigate their equipment and lines. Secondly, if the voltage at the main service panel is within the normal range, then the issue lies within the building's electrical distribution system. In this case, proceed to check the load in the main service panel. Use a clamp-on ammeter to measure the current on each phase of the main service conductors. Add the current readings from each phase to determine the total current draw. Compare the total current draw to the rated capacity of the main service panel and the main service conductors. If the current draw is close to or exceeding the rated capacity, the system is overloaded. Identify and reduce non-essential loads to alleviate the overload. Thirdly, if the load in the main service panel is within the rated capacity, inspect all connections in the main service panel and downstream panels. Look for loose connections, corroded connections, or signs of overheating. Tighten any loose connections and clean corroded connections. Replace any damaged or deteriorated wiring. Fourthly, investigate the individual circuits and equipment connected to the affected panels. Use a multimeter to check the voltage at various points in the circuits. Identify any circuits with excessive voltage drop, indicating a problem with the wiring or connections. Check the current draw of individual equipment and compare it to the nameplate rating. Identify any equipment drawing excessive current, which could indicate a fault or malfunction. Fifthly, consider the impact of any recent changes or upgrades to the building's electrical system. For instance, if new equipment has been installed, it may be drawing more power than the existing system can handle. In this scenario, it was mentioned that 2 elevators are being upgraded. This is a potential source of the low voltage issue. Consult with the elevator upgrade contractor to determine the power requirements of the new elevators and whether the existing electrical service is adequate. The upgrade may have introduced a significant load that the transformers are struggling to handle, even if each transformer is rated at 2000 kV amps. This is because the inrush current during elevator motor starts can be several times the running current, causing a temporary voltage drop. To calculate the approximate full load current for a 2000 kV amp transformer, assume a 3-phase system with a voltage of, say, 480 volts. The formula is I equals S divided by the square root of 3 times volts, where I is the current, S is the apparent power in volt amps, and volts is the voltage. Thus, the current would be 2 million volt amps divided by the square root of 3 times 480 volts, which is approximately 2405 amps. This is the full load current the transformer can supply. However, elevator motors can draw significantly more current during startup. This inrush current can cause a voltage sag, especially if the transformer is already near its capacity or if the building's electrical system has high impedance. Check the transformer impedance. Lower impedance transformers will typically handle motor starting loads better than higher impedance transformers. The transformer impedance is usually expressed as a percentage on the transformer nameplate. Next, regarding the elevators, check the motor starting methods. Traditional across-the-line starting can cause significant voltage dips. Consider using reduced voltage starting methods such as soft starters or variable frequency drives, often called volts FDs, to reduce the inrush current and minimize voltage sags during motor starts. Also, evaluate the power factor. Low power factor can increase the current drawn from the transformers, leading to voltage drops. Consider using power factor correction capacitors to improve the power factor and reduce the current demand. You could monitor the voltage at the main service panel and at the elevator motor terminals during elevator operation. Use a data logger to record the voltage fluctuations over time. This will help identify the magnitude and duration of the voltage sags. Also, check the transformer loading. Use thermal monitoring to ensure the transformers are not overloaded. The overloaded transformers can experience excessive temperature rise, leading to premature failure and voltage regulation problems. Next, review the building's electrical system one-line diagram to understand the distribution of power and identify potential bottlenecks or weaknesses. Ensure that the electrical system is properly grounded and bonded to minimize the risk of ground faults and voltage fluctuations. Inspect the grounding system for corrosion or damage, and repair or replace as needed. Verify that all electrical equipment is properly installed and maintained in accordance with the manufacturer's recommendations and applicable electrical codes, such as the National Electrical Code, often called the NEC. Ensure that all electrical work is performed by qualified and licensed electricians. Consider consulting with a qualified electrical engineer to perform a comprehensive power quality study of the building's electrical system. A power quality study can identify potential problems such as harmonics, voltage imbalances, and transient voltages, which can contribute to low voltage issues. If the low voltage issue persists, consider installing a voltage regulator or a constant voltage transformer to stabilize the voltage supply to critical equipment. Voltage regulators and constant voltage transformers can compensate for voltage fluctuations and maintain a stable output voltage. Also, implement a preventative maintenance program for the building's electrical system. Regularly inspect and test electrical equipment to identify and address potential problems before they lead to failures or low voltage issues. Keep detailed records of all inspections, tests, and maintenance activities. Check for loose or corroded connections not only at the main service panel but also at all distribution panels, circuit breakers, and equipment terminations. Even seemingly minor corrosion can significantly increase resistance and contribute to voltage drop. Be especially diligent in areas prone to moisture or temperature fluctuations. Measure voltage drop across various segments of the electrical system. This can help pinpoint areas with excessive voltage drop due to undersized conductors or high impedance. The National Electrical Code, often called the NEC, provides guidelines for maximum allowable voltage drop in branch circuits and feeders. Refer to NEC section 210.19 and 215.2. Use a power quality analyzer to capture and analyze voltage waveforms. This can reveal hidden problems such as harmonics, transients, and voltage sags that may not be apparent with a standard voltmeter. Harmonics can cause overheating of electrical equipment and contribute to voltage distortion. Transient voltages can damage sensitive electronic equipment. If UPS units are frequently switching to battery power, this is a strong indicator of voltage fluctuations or power quality problems. Investigate the cause of these fluctuations rather than simply accepting them as normal operation. Check the UPS event logs for detailed information on the nature and frequency of power disturbances. Ensure that all sensitive electronic equipment is protected by surge protection devices. Surge protection devices can help protect equipment from damage due to transient voltages caused by lightning strikes or switching events. Coordinate with the utility company to investigate potential problems on their side of the service connection. The utility company may be able to identify and correct issues such as voltage regulation problems or equipment malfunctions on their distribution system. Consider the impact of other large loads in the building, such as HVAC systems, pumps, and manufacturing equipment. These loads can cause voltage dips when they start up or cycle on and off. Implement load shedding or demand response strategies to reduce the impact of these loads on the electrical system. Also, review the building's electrical load profile to identify opportunities for energy efficiency improvements. Reducing overall energy consumption can reduce the load on the electrical system and improve voltage stability. Ensure that the building's electrical system is adequately sized to meet the current and future needs of the building. If the building has undergone renovations or expansions, the electrical system may need to be upgraded to handle the increased load. If the building is served by multiple transformers, check the load sharing between the transformers. Uneven load sharing can lead to overloading of one transformer and voltage regulation problems. Use thermal imaging to identify hotspots in the electrical system. Hotspots can indicate loose connections, overloaded conductors, or equipment malfunctions. Regularly calibrate test equipment to ensure accurate measurements. Inaccurate measurements can lead to incorrect diagnosis and ineffective troubleshooting. Document all troubleshooting steps and findings. This will help track progress and avoid repeating the same steps unnecessarily. Share troubleshooting information with other members of the maintenance team to improve overall knowledge and efficiency. Consider using a computerized maintenance management system, often called a CMMS, to track maintenance activities and manage electrical equipment. A CMMS can help schedule preventative maintenance, track equipment performance, and manage inventory of spare parts. Also, provide training to building occupants on how to identify and report electrical problems. This can help identify potential problems early before they escalate into major issues. Communicate regularly with building occupants about the status of the electrical system and any planned maintenance activities. This can help manage expectations and minimize disruptions. If necessary, consider hiring a qualified electrical contractor to perform a comprehensive inspection and testing of the building's electrical system. An experienced contractor can identify potential problems that may not be apparent to in-house maintenance staff. Always prioritize safety when working on electrical equipment. De-energize circuits before working on them whenever possible, and use appropriate personal protective equipment, or often called PPE, such as insulated gloves and safety glasses. Follow lockout-tagout procedures to prevent accidental energization of circuits. It's crucial to remember that electrical systems are complex and potentially dangerous. If you're not comfortable working on electrical equipment, seek the help of a qualified electrician. Improperly maintained or repaired electrical systems can pose a serious risk of fire, shock, and injury. Ensure that all electrical work complies with applicable electrical codes and regulations. Electrical codes are designed to protect people and property from electrical hazards. Regular inspections and maintenance are key to ensuring the safety and reliability of the building's electrical system. A well-maintained electrical system can help prevent costly downtime, improve energy efficiency, and extend the life of electrical equipment. Consider the impact of the building's location on the electrical system. Buildings located in areas with frequent lightning strikes may require additional surge protection. Buildings located in coastal areas may be more susceptible to corrosion. Buildings located in areas with extreme temperatures may require special insulation and ventilation. Also, review the building's insurance policy to ensure adequate coverage for electrical damage. A comprehensive insurance policy can help cover the cost of repairs and replacements in the event of an electrical failure. Maintain a detailed record of all electrical equipment, including manufacturer, model number, serial number, and installation date. This information can be helpful for troubleshooting and ordering replacement parts. Keep a readily available supply of spare parts for critical electrical equipment. This can help minimize downtime in the event of a failure. Consider using a backup generator to provide power during outages. A backup generator can help keep critical equipment running and prevent disruptions to building operations. Ensure that the backup generator is properly maintained and tested regularly. Also, develop an emergency plan for dealing with electrical failures. The emergency plan should include procedures for shutting down equipment, contacting emergency services, and evacuating the building if necessary. Communicate the emergency plan to all building occupants and conduct regular drills. If the low voltage issue is affecting sensitive electronic equipment, consider using a power conditioner to improve the quality of the power supply. Power conditioners can help filter out noise, correct voltage fluctuations, and protect equipment from damage. Consider the impact of the building's grounding system on the performance of sensitive electronic equipment. A properly designed and installed grounding system can help reduce noise and improve the reliability of electronic equipment. Regularly inspect the grounding system for corrosion or damage, and repair or replace as needed. Ensure that all electrical equipment is properly labeled with voltage, amperage, and wattage ratings. This information can be helpful for troubleshooting and preventing overloads. Use appropriately sized conductors for all electrical circuits. Undersized conductors can cause voltage drop and overheating. Refer to NEC Table 310.15 for conductor ampacity ratings. Ensure that all electrical boxes are properly sized to accommodate the number of conductors and devices. Overcrowded electrical boxes can cause overheating and create a fire hazard. Use appropriate wiring methods for all electrical installations. The NEC specifies different wiring methods for different applications. Ensure that all electrical connections are properly made and tightened. Loose connections can cause overheating and create a fire hazard. Use appropriate tools for making electrical connections. Improperly made connections can cause overheating and create a fire hazard. Inspect electrical equipment for signs of rodent or insect infestation. Rodents and insects can damage electrical wiring and equipment. Seal any openings in the building's electrical system to prevent rodent and insect entry. Use appropriate pesticides to control rodent and insect populations. Consider the impact of the building's lighting system on the electrical load. Energy-efficient lighting systems can reduce the overall electrical load and improve voltage stability. Use LED lighting fixtures to reduce energy consumption and improve lighting quality. Install occupancy sensors to turn off lights in unoccupied areas. Use daylight harvesting systems to reduce the need for artificial lighting. Consider the impact of the building's HVAC system on the electrical load. Energy-efficient HVAC systems can reduce the overall electrical load and improve voltage stability. Use variable frequency drives, often called volts FTs, to control the speed of HVAC motors. Install programmable thermostats to optimize HVAC system operation. Use energy recovery systems to reduce the energy consumption of HVAC systems. Consider the impact of the building's plumbing system on the electrical system. Leaking water can damage electrical wiring and equipment. Repair any leaks in the building's plumbing system promptly. Install ground fault circuit interrupters, often called GFCIs, in areas where water is present. Consider the impact of the building's fire alarm system on the electrical system. The fire alarm system must be reliable and operate properly during a power outage. Ensure that the fire alarm system is properly maintained and tested regularly. Use a backup power supply for the fire alarm system. Consider the impact of the building's security system on the electrical system. The security system must be reliable and operate properly during a power outage. Ensure that the security system is properly maintained and tested regularly. Use a backup power supply for the security system. Consider the impact of the building's data and communication systems on the electrical system. Data and communication systems are sensitive to power quality problems. Use surge protection devices and power conditioners to protect data and communication equipment. Ensure that the data and communication systems are properly grounded. Consider the impact of the building's elevator system on the electrical system. The elevator system can draw a significant amount of power, especially during startup. Use energy-efficient elevator motors and control systems. Install regenerative braking systems to recover energy during elevator braking. Consider the impact of the building's other equipment on the electrical system. Large motors, welders, and other equipment can cause voltage fluctuations. Use power conditioners and surge protection devices to protect sensitive equipment from voltage fluctuations. Ensure that all equipment is properly maintained and operated. By systematically investigating and addressing these potential causes, the root of the low voltage issue can be identified and resolved, ensuring a stable and reliable power supply for the building.